So yeah, we're very lucky to have Dr. Emma Chapman come to us from just down the road in Imperial this week. Emma is an expert in all things reionization, and that's what she's ultimately going to talk to us about. She's got her original master's up in Durham, like all the best people, before legging it down south to London to study for a PhD at UCL as well, where she also did her first postdoctoral, held her first postdoctoral position. Ultimately made the shorter jump over to Imperial, where she's held a series of prestigious fellowships, including the Royal Astronomical Society Fellowship and most recently the Royal Society Dorothy Hodgkin Fellowship, I believe. Is that right?
Yep.
Yeah, great. So yeah, Emma, please take it away.
Okay, thank you. Thank you for inviting me, firstly. I'm going to be talking about, the first stars and why we care about them and how we're going to look for them. I'm going to start off with a kind of what might be perceived as an outreachy introduction, so please don't see this as condescending. It's because I think it's important to set the context for research before you get really into the nitty-gritty. I'm going to start, really, really outreachy and say, what do we know about light? Light is really, really fast. We know this as astrophysicists. We use it in our everyday workings. So we know that if we were waving to our friend on the moon, then it would take only 1.3 seconds for that light to get to the moon and 1.3 seconds to get back. So we wouldn't see a delay. We'd see our friend waving back and we'd be super happy. Going on Mars, though, of course, we've found out from the not found out, but we've experienced with the Perseverance that it takes 4 minutes for light to come back from Mars. So by that time, we're pretty sad because the delay in the wave has gone far too long, and we think our friend doesn't love us anymore. If we go back even further, let's go to the Andromeda galaxy, one of the nearest galaxies, and we give our alien friend a good wave, and our alien friend gives us a good wave back. Then the problem is the light takes so long to get to us that we're not only very sad, we're actually very dead. And that's a problem. But what's not a problem here is that we have a way of looking back in time. Because light does take 2.5 million years to get from Andromeda to us, we're seeing it as it was 2.5 million years ago. So we have this really, really handy way of looking back in time. And using that, we've managed to be pretty smug about what we've filled in the lifetime of the universe. We know plenty about the Earth, we know plenty about Mars, we know plenty about the Moon. Of course, there's always more, but we're getting there. And we've pushed even further back, which is not working. Why have I stopped? There we go. We've looked even further back. We've got beautiful images and science out of the closest galaxies and pushing further back in time as well. And we've even got the Hubble Deep Field, for example, and associated new observations, which push right back into the Epoch of Reionization, which I'll come into later, which is 800 million years after the Big Bang. So not to scale, obviously. And of course, we all know that we're probably all fans of the Big Bang, hopefully. And we've got lots of evidence to support that for cosmic microwave background. So we've got images from 380,000 years after the Big Bang. So we can be pretty smug about filling in the timeline and think that we've managed to do it all, except there's this little bit in the middle where we clearly haven't filled it in yet. And this is called the era of the first stars, and it lasts from around 380,000 years after the Big Bang to about 800 million, a billion years after the Big Bang. We don't really know much about it at all. That's a very big amount of time to be missing in terms of the evolution of our universe. So if we want to understand how our universe has evolved, how the stars have evolved over their generations, then missing this huge chunk of the timeline could be perceived as being a pretty big problem. Because what that really amounts to is missing that amount of time from around 400,000 years after the Big Bang to around a billion years after the Big Bang. That's equivalent in the human lifetime to missing from around your moment of birth to your first day of school. So that's how much we're missing in terms of the evolution of our universe. And if you consider how formative those years were, what effects they had on your later life, it's no wonder that we're very, very keen on finding out what happened in that time cosmologically, so we can better inform what we're understanding locally, both in time and in distance. So what do we know? Well, we know that very early on after the Big Bang, these first stars didn't just pop out fully formed. We didn't get the first stars, the first galaxies just popping out of the Big Bang. It's far too hot, there was far too much going on. So all we really had were the most basic elements like hydrogen and helium and a heck of a lot of photons wandering around. So we can immediately say, tick box. When I'm doing outreach, I try and evidence this a lot more and say, look, there was a Big Bang, but I won't bother here. There were first stars. So that's our first thing that we want to say, is that what we look for ultimately is evidence of the first stars, and studying the Epoch of Reionization is just one niche way that we do that. So the reasons to care, as I've already mentioned, we've got a huge amount of missing data and a huge potential to fill in all of that data and make some conclusions about the time closer to us. So the example I normally use is the supermassive black hole growth over cosmological time, and how we might be able to get an indication of how these supermassive black holes grew so large, so massive, by looking at those first, as we'll see, very massive stars, and how they might have formed massive black holes very early in the universe and kind of jump-started that growth. So there's lots of conclusions that we can hopefully correct or add to by filling in this data. The second reason we care, the reason I care particularly, is that the first stars are extraordinary. So they are worth studying in their own right because they're fascinating. So here is the sun, very beautiful, very lovely, very yellowy orange. And here is a terribly PowerPoint filtered artist's impression of a first star. First of all, you'll notice that it's a lot bluer. That's because we think that these stars were a lot hotter. So around, what was it, 1,000,000 Kelvin on their surface temperature, as opposed to, the 5,800 Kelvin of our sun. But the main thing that really one of the main things that really differentiates them is their mass. So we've done lots of different simulations on this, including in your group, and there has been more and more evidence that these first stars were very massive. So up to 100 times the solar mass. There has been simulations that have gone up to 1,000 solar masses. That's harder to reproduce. And more recently, there's a lot more simulations showing that these stars didn't just form out singular massive stars, but actually in nurseries. So where you have a very large, massive star in your central area, but actually then you get your sibling stars forming of much lower mass, of around 80%, 90% the solar mass. Which I don't think I'm going to have time to talk about it, and it's not particularly my area, but which is what gives birth to the absolutely fabulous field of stellar archaeology, and the idea that you might still have these stars around. So yeah, they're more massive. Yes. So as we probably all know, there's this lovely mass lifetime relationship when it comes to stellar evolution, in that the higher mass your star, then the shorter its lifetime, because it simply guzzles through its hydrogen much faster. So the first stars are projected to have lifetimes of around only 1 million years, as opposed to the sun, about around 10 billion years-ish. So that's the other reason that they're very different, and it's also the reason that they're very interesting to try and find in the way that we're going to talk about today, because obviously if you've got lots of these wonderful first stars, a completely different species really, and they're all from 13 billion years ago when they form, then you're in trouble because they're all dead about 1 million years later. And so probing them directly is it's an impossible thing to do, except of course if you've got a few of those first stars which are around 80% of the solar mass, which will mean that they have lived 13 billion years and might still be around in our Milky Way, which is what stellar archaeologists are trying to uncover at the minute. So the first stars are extraordinary. They're an extinct species, possibly. So definitely worth looking at in terms of, even if you're just interested in stars themselves, and they're very interesting to look at. But the third reason, cosmologically speaking, is that they changed the universe. So they were responsible for one of the major changes in our universe in terms of metallicity. So as I said, early in the universe, sorry, after the Big Bang, you've got just hydrogen, just helium, smidge of lithium. You can't build much more because there's just too much going on, too hot, too energetic. And so it takes a lot longer for the universe to kind of cool down and let these first stars form around, we think, 180 million years after the Big Bang, evidenced by an experiment which I'll talk about at the end if I've got time. But so when these first stars form out of this early hydrogen coalescing, then it is just hydrogen and helium. So we call them metal-free. We call them metal-free stars. And as the universe goes on, what we've found decades, in the 20th century was that we can divide the stars we see in the Milky Way and further into these different populations. So you've got stars like the Sun, which are metal rich, so they have a fair few heavier elements in them. And then you've got your older stars, which are metal poor. And so it didn't take too much imagination in the mid 20th century to say, well, what happens if we project that backwards, and what happens if we get these metal-free stars? And that kicked off the search for population-free stars, of which none have ever been observed so far. Yes, but it is the population-free stars which are responsible for kick-starting this evolution of metallicity in the universe. And that is obviously through their fusion. So they fuse their hydrogen, they fuse their helium, they create heavier elements, which when they explode in probably very bright supernovae, then they expel all of those heavier elements out into their environment and immediately pollute it. So much so that you cannot, by definition, form another metal-free star because the gas is too polluted, and you immediately form the population-2 star in that local area. Not immediately form the star, but the next star that forms when the gas is settled, then that will be a population-2 star. So it is these first stars which really begin producing the building blocks that we need to go from a very dark, very boring, very black universe. It doesn't seem to have much going on to the visible eye, to a universe which has a huge amount of structure and diversity and color and elements, huge number of different elements. And so it's these first stars that really started that. Through this change as well, they also created another phase change in the universe, which we'll start talking about in a moment. They were extraordinary. All of this comes together to the fact that these first stars are well worth looking for and learning more about for themselves, because they're just very interesting in terms of their stellar capacity, but also in terms of how they change the universe cosmologically and phase changes. How can we look for them? As I've said, we've never directly observed never indirectly observed a population-3 star or metal-free star or first star, however you want to call them. So the aim of the game is to go from an awful artist's impression to something a little bit more solid. How can we learn more? Well, probably the only one that I'm actually going to have time to talk about today, aside from stellar archaeology, is looking back in time, which is what a lot of us do. So I don't really need this slide, but yes, we're all quite used to the idea that you look further in distance and you look further back in time, but it's easy to forget how mind-blowingly cool that is. And when it comes to this area of research, we really push it to the limit, in which we are looking so far back that we are detecting light that is 13 billion years old from around these first stars. That light, if we were trying to detect the light from those first stars optically, it's far too faint for us to be able to observe with optical telescopes, things like that. So instead, what we have to use is a different form. So what we use is radio telescopes. We use these radio telescopes not to detect these stars themselves, because again, the signal in terms of radio is again very faint from the individual stars, but of the impact they have on their environment. So these first stars not only do they drive the metallicity change in the early universe, they also drive the final phase change of hydrogen in our universe, and they do that by heating. They heat the hydrogen, they ionize the hydrogen until we get to a predominantly ionized hydrogen universe. And so by detecting emission from around the first stars, we can infer what these first stars were like. The Epoch of Reionization, horrible name. What it is the period from around 400 million years after the Big Bang to around 1 billion years after the Big Bang. The reason I'm so vague on that is because we don't particularly know all of these labels of within the era of the first stars. You've got the Dark Ages, which is from after recombination to whenever the first stars formed, and then you've got the tiny bit that we call the cosmic dawn, which is when the first stars switch on. Then you've got the Epoch of Reionization, which is when all the hydrogen is ionized. Around redshift 6, we think that ends. So we've got a lot to fill in. We've got all of this to fill in. I'm going to be focusing just on the Epoch of Reionization, possibly a little bit on the Dark Ages towards the end. And the great thing about hydrogen is that it produces a heck of a lot of radiation. And at very particular wavelengths. So it produces radiation at 21 centimeters in wavelength, which is very handy because by the time it arrives to us on Earth, it has been redshifted to wavelengths of around a meter, 2 meters, around 2 meters, sorry, in wavelength, which makes it absolutely ideal for detecting with radio telescopes such as LOFAR, which is the one that I mainly use. Okay, so we know that we need to fill in a huge amount from this time. Why aren't we going forward? There we go. What do we know so far? Well, we can learn a lot from the CMB. We can learn a little bit from how the photons traverse the universe from the cosmic microwave background and how they are scattered by all the free electrons between them and when we detect them, between the CMB and when we detect them. So what we're talking about here is if you have a much earlier reionization, so let's say the first stars form, there's a heck of a lot of them, they form galaxies really quickly, they ionize all of this hydrogen very, very quickly, then what will happen is they will produce there'll be a lot more ionized hydrogen, so lots of free electrons much earlier in the universe, which will mean these CMB photons, as they're traversing the universe, there's lots more electrons for them to get scattered by. What this results in is a higher optical depth measurement from the CMB maps. So when you can determine this optical depth, then it comes out as a lot higher if it's been scattered a lot more. You've got a much later reionization, so either the first stars switched on a lot later, or they were very weak in their radiation levels, or anything like this. Then you've got a later reionization, less electrons, low optical depth. So from the Planck measurements, then what we determine is that the optical depth that they determine is it works out at a reionization that took only around 0.5 million years. I want to say billion, 500 million, yeah, 0.5 billion years, I was meant to say. Yeah, so it was very, very fast. It was faster than we expected it to be. So we can tell a huge amount from the CMB, which is great. So we know that it was quite rapid. What that means, we've not quite figured out yet. The problem is that the CMB, to determine the reionization parameters, you have to assume a very sudden reionization, and that's not necessarily what happened. Okay, so in terms of what we know from other I'm trying to think, constraints. Sorry, other constraints we have. Quasars are a really useful tool, and the reason is that they at high rate or at any redshift they produce a lot of broadband emission, and when you have them at high redshift, then as this emission comes to us on Earth, then every time it encounters a cloud of neutral hydrogen, then any photons that have been redshifted into the Lyman alpha resonance will get absorbed, and you will get a dip in the emission, the spectra that you measure from the quasar. So the more neutral hydrogen clouds you have, then the more dips you have, and eventually, if actually this quasar is at quite a high redshift, and it's got lots and lots of neutral hydrogen because the universe hasn't been reionized enough, and you get lots of these. You get a trough basically. So this can tell us a lot about the state of the universe. If you observe quasars at very high redshifts and they've got what we call a complete trough, that means that they've still got lots of neutral hydrogen around them. So what you really want to look at is at the point at when your trough starts to become more complete, because that means that your universe has become lots more neutral, and that's kind of when reionization ended. And so we think that gives us a constraint of around 6, actually thinking it might be about redshift 5.5 now. So we think that reionization is over by around that redshift. So we've got 2 major constraints, one on how quick it was and one on when we think it ended. That's about it in terms of the major constraints about what we know. So we need to come up with a very different way of finding out what's going on. And we do this by looking at ionized bubbles in the hydrogen. What we see is what we see in simulations, I should say, is very different ways of reionizing the hydrogen according to what kind of sources are around in the early universe. So for example, here on the left, we've got the higher redshift universe, so 13 billion years ago. And on the right, we've got 1 billion years later, so when reionization ended. So it's a bit of an odd color scheme, but in the purpley dark colors, what you've got is neutral hydrogen, and in the green, you've got ionized bubbles. And so what you see is that on the left, you start to get these first sources ionizing bubbles, so ionizing all the hydrogen around them in spherical shells, and then we call it an ionized bubble. And if you've got just stars, then what you find is quite neat, quite small bubbles that take quite a long time over this billion years to really grow and coalesce and form a reionized universe. If you've got quasars, then what you find is that it's very, very quick, is that your bubbles are much larger, they're much more freeform, and they coalesce much quicker into an ionized universe. But of course, the chances are is that you've got a mix of both. You're not going to have just one in the early universe. So the chances are that you're actually going to have a model which have a mixture of both. This is really good because it means that we can observe these bubbles and try and actually infer what was in them. So what does it really look like? Well, when you're looking with a radio telescope at hydrogen, it doesn't really compare to, for example, optical Hubble Space Telescope images. On the left, we've got what you would see in the dark ages, which is just emission everywhere. So this is all your hydrogen emission, all your 21 centimeter photons that you're measuring. That's on the left here. So you've got nothing much going on in terms of bubbles. Then you've got the cosmic dawn, and you've got these first stars starting to form ionized bubbles. And if you've just got stars, then they actually form what we call the Swiss cheese model, which is just emission, which has got lots of nice, neat bubbles in it. And then when you get the first galaxies forming, then you get much, and black holes as well, quasars, then you get much freer form bubbles. They coalesce much quicker. And so eventually you get to the end of the Epoch of Reionization and you've got all black, you've got no emission at all. It's an absence, it's a detection of absence, if you will. What we're trying to do is we're trying to detect the bottom row and infer backwards of what was in there from either the shape or the number of bubbles and how they change over redshift. And we'll be able to do this over the whole billion years-ish that we're missing from our cosmological timeline. Well, the reason we're going to be able to do this is because we've got some pretty awesome telescopes. This is LOFAR, looks quite underwhelming, but under those black tarpaulin tiles are lots of these bow tie antenna. And this is in wetlands in the Netherlands. It takes forever to get to. And it's in the absolute middle of nowhere, and it's just surrounded by a moat with lots of birds. But it's beautiful in its own way. And what it is a radio telescope, and it's an interferometer. And so as underwhelming as that looks, actually there's around 1,300 of those antennas spread around Europe and, well, I guess the UK now. So we've got them everywhere. They're mainly based in the Netherlands, so most of them in the Netherlands in a core formation, we call them, but they do spread out across very long baselines in order to get a much higher resolution image for when that's needed. The LOFAR is a really powerful telescope. It's been going since 2011. We've been taking data, so 10 years now. 10 years of data, still going. And I'll get on to why we're still going now, really. What I do is foreground mitigation in terms of my contribution to the LOFAR collaboration. So what are we actually trying to observe with LOFAR? What I showed in terms of the images and the bubbles, even as low tech as that looks, that's actually still out of our reach at the minute, because LOFAR doesn't have high enough signal to noise to do that. So that is the realm of the square kilometre array, which I'm also involved in and very excited about, but I don't really have much time to talk about it in this presentation, at least. For LOFAR, what we're looking for is a statistical signal. And what we've decided is a good statistic is the power spectrum. So on the x-axis here, you've got your wave number, your K, your scale, and then on the y-axis, you've got your averaged 3D power spectrum. So taking your cube and Fourier transforming it in spherical shells and forming your 3D Fourier transform in that way. And what I've got here is a cartoon of two different reionization models, because we really don't know what was going on. We can guess that there were stars at this point, quasars at this point, mix them all up and hope. But it turns out there's a huge number of models. So here I've got, for example, star-dominated reionization and quasar-dominated reionization. As you can see, they give you different power spectra. There we go. When you add noise, the system noise of the telescope is around 10 times as large as the signal from the cosmological signal. So we're already losing the battle in terms of signal to noise, and it changes the power spectrum so that at the higher K scales where the noise is going to dominate, then these models become unable to be differentiated. Ooh, when you add foregrounds, you're in real trouble. The foregrounds dominate the cosmological signal by around 3 to 5 magnitudes. And as you can see, when you add all of that in, then you really can't differentiate these models at all. So you can't really learn much at all. And this is the signal that we detect. So this one at the top, the stripy signal, that's what we actually detect. And so it's about getting science out of that and about understanding how to get down to the fainter line so we can actually do some cosmology and get some astrophysics out of this. So how are we going to do that? Well, luckily for us, the cosmological signal and the foregrounds have a very different form. So this is a line of sight in what we call a brightness temperature box. So that can just be kind of seen as the intensity of the 21 centimeter radiation. So it's temperature. And if you look along the line of sight of the simulation box, this is what you will see across frequency, or equivalently redshift. So the x-axis is frequency, which you can also think of as the redshift. It's just that we've switched to observational parameters now, because we're simulating our telescope. And so as you can see, it's very decoherent over frequency. It's very rough. And so what we see over time, over redshift, is at the very low frequencies, so high redshift, then you've got this signal going everywhere because you've got lots of different bubbles, you've got lots and lots of hydrogen. And then towards the end frequencies, which is your lower redshift, then it starts to flatline. And that's because there isn't any hydrogen to get 21 centimeter photons from the redshift. Then you add your noise in, as I said, it's quite a bit bigger. Same kind of form though, decoherent over frequency. And then you need to add in your foregrounds. So there's plenty of them. to simulate and add. You've got all of your galactic stuff, so your galactic synchrotron, your galactic 3-3, your supernovae remnants, and then you want to go into your extragalactic foregrounds as well, which are less overwhelming but still there. And all of that overlays your lovely signal that you're trying to find. And so when we look at this line of sight, just a typical line of sight, then this is what the foregrounds look like. They're much, much larger. The cosmological signal, you can barely see anymore. It's a straight line, basically. But what you notice is they have a very different shape. So the foregrounds are very, very smooth along frequency when you simulate them in this way. So that gives us a really good way of differentiating these, because when you add all of these together, what you get is you get your noise imprinting on your signal, but it keeps this kind of this power law shape. And so that indeed is what people did 10 years ago. They looked at this in simulations and they said, aha, I know what we can do here. We can fit a smooth function along frequency. We can form a model for our foregrounds. We can subtract it off and get back to our noise and cosmological signal. And there are ways of dealing with noise. Magic. There are ways that you can remove your noise off your signal. So that's less of a worry, which I'll get to later, as why that might not be so small a worry. But the aim was 10 years ago was that would be easy to deal with, and you'd end up back with your cosmological signal. And so in terms of power spectra, what you would end up getting is you'd remove your foregrounds, you'd deal with your noise, and you'd end up with a distribution of recovered cosmological signal points, which would suggest one or either of, well, there's not just two models. It would differentiate between the multiple models that there are out there for reionization, and you could do some real science from it. You could look at what was there. Now, the problem is that the foregrounds aren't necessarily smooth. So we've said that they are smooth, and that's because if you simulate them through just the kind of the physical synchrotron processes, etc., then yes, you get a smooth function over frequency. But if you add a wiggle, and there can be plenty of wiggles. So for example, polarization leakage in the instrument. If you have polarization leakage between the different polarization channels, so from your Stokes Q or Stokes U into your total intensity or back, then you lose some of your signal, and that's not predictable over frequency. You don't know it's happening, so you can lose that, and it roughens the signal. It gives a little wiggle, and if you don't model that correctly, then that can start to bias your results. So you think you've got your recovery, but actually you haven't. It's a false recovery. It's a biased recovery. And so this polynomial removal, as we call it, fitting this smooth function, subtracting it off, only really works if your instrument is perfect. It's very unlikely. Okay, so we come on to my PhD really, which is what we started with and have progressed ever since, which is blind source separation methods. These methods don't assume a particular form of the foreground, so like a nice smooth polynomial. They don't assume that at all. What they instead do is use statistics to separate out all these different components and try and form a model for the foregrounds. The blind source separation methods that I've used and developed over time have worked on what we call the mixing model, which is this very simple equation at the top. And the idea is that you have an observed data, which is your X, and that this can be broken down into a series of statistically independent components, which is S. And you can think of your data being made of all of these different components added up in different amounts, which is what your mixing matrix tells you. It tells you how much of each statistical component add up to make this data with your noise on top. So what we want to do is reverse this equation really, and we want to figure out what these independent components are. The way we do this with fast ICA, which is fast independent component analysis, the way that works is using the fact that if you have a probability distribution function of a signal, then the theory goes that the more components, the more statistically independent components you have in data, then if you take the probability distribution function off that data, it will be more Gaussian. So if you've got two very different, and they can't have anything to do with each other, statistically independent components, then they will form different PDFs, so non-Gaussian PDFs to some degree. Mix those two independent components together though, and your PDF becomes more Gaussian. What we want to do is reverse that. We measure a signal which will have a more Gaussian probability distribution function, and you play around with it, you iterate, you separate out these signals until you have two signals, two statistically independent components, which are as non-Gaussian as possible. And when you have those components that are as non-Gaussian as possible, then you can be confident that you have found the most statistically independent components of that combined signal. So for us, what's useful is actually, yeah. So for us, you don't just have to have two components. By the way, you can choose your number of components, which is kind of where the human comes into this process. So whereas I said it doesn't assume a particular model, you do have to assume a particular number of components. So that's something that you can play around with. If we visualize this on the left here, we've got the total data. So this is kind of what the foregrounds plus the cosmological signal plus the noise looks like in terms of a single image taken at say 150 megahertz. This is what it would look like. And that's basically just foregrounds because the other stuff is so small. And then in the vertical column here, what I've done is I've used FastICA to separate that out into 4 different components and visualized a mixing matrix full of numbers of how much of each one of these slices makes up this into colors. And then you add your noise on, and this is how you break down your data. So the first thing to notice is that those independent components don't particularly look like foregrounds plus cosmological signal. We don't separate out, unfortunately, independent components don't relate to the contributions to our signal because they're not necessarily independent. So the galactic synchrotron might not be independent of the galactic free, for example. So actually our cosmological signal lies with the noise because, well, yeah, because a bit of a black box in terms of this, but because the cosmological signal is so small, because it's not as smooth as the other components, then it ends up with the noise. And so what you actually get from this is almost we take advantage of the fact that this method doesn't work and it forms in this AS part a foreground model. And so using that foreground model, we can then subtract that off and get our cosmological noise. So you can almost see this AS, this middle bit here, as a fitting of less assumptions than the polynomial removal. So there's one other method that I just want to talk quickly through, which is generalized morphological component analysis. I'll go through this quickly because it's the same kind of thing. You're using a mixing model, but this time you're not using statistical independence, so looking at these PDFs, you're looking at a morphological independence, which means looking at how different their spatial structure is. The idea behind this is what you do is you try and form a sparse basis set for your different components. So what you need to do first before using this method is you decompose your signal into different wavelet scales. So you do a wavelet decomposition, and that's what I've shown here. So the biggest squares on the left is cosmological signal, and on the right is some foregrounds. And what I've just shown you is 4 wavelet scales in that decomposition that I've done. So you've got your larger scales, and then you've got your smaller scales in the smaller square. And the idea is that you can represent these signals in terms of the contribution of the different scales in very different ways. So the cosmological signal, for example, will have more contribution from your smaller wavelet scales than your foregrounds, which are larger in terms of their scales in the sky. And so the idea is that your representation of these two components in wavelet space will be so different that you can separate these things out. That's how GMCA works. So the idea is that using these blind source separation methods, we can take into account the unsmooth foregrounds. So even if you have this wiggle on your foregrounds, these methods recognize that. They recognize them as part of the independent components that they predict in the models. And so we end up, hopefully, theoretically at the moment, we end up being able to push down to a detection of that statistical signal and start to infer which models that we're using. Okay, so this is where we are. We're not quite there yet. On the x-axis, oh gosh, am I running out of time? Been talking for a while. How much time have I got left on?
About 5 minutes, something like that.
5 minutes. Okay, no, that's cool. I'll yeah, that's not too bad. Okay, so on the x-axis here, we've got the redshifts over which all of these different radio experiments work. The epoch of reionization is from around redshift 12 to redshift 6. And so LOFAR is in the diamonds. I just added one of our latest ones in yellow, so we can see that we're pushing down. But what you can also see is that we're not there yet. So this is one of the, the random 21 centimeter fast models that we can have. We're not there yet. Cosmic Dawn as well. We've got a few constraints there, but we're getting there. But it's been 10 years. So what have we been doing? Well, the problem has been a couple of things. One, with these blind source separation methods, what we found is there is a scale dependence to them, which means that what they do is that they assume a single mixing matrix, so a single A in that equation for all the scales of the data. So it's just one single matrix. You don't break that down according to the scale of the data or according to anything. And so what happens is that, as I said, there's a human element, as it were, where you choose the number of components and you have to decide which number of components fits your data best. And of course, you can use different ways of evidencing this. But here, what we're showing is that to fit the foregrounds the best that we can, we need say 10 components to our foreground model, because the foregrounds that we actually detect are so complicated. They've got so many instrumental effects in that we didn't particularly expect. So polarization leakage, frequency dependence of the instrument, so the resolution changes over frequency, that causes something called mode mixing. So what you get is lots of large scale foregrounds thrown up into lower scales of the power spectrum. It all mixes up. It's basically, they don't stay smooth as much as we would like. So we need lots of components to model them well. But the higher number of components that you start to add, like most methods, anything really, the more you fit, you overfit. And so with a cosmological signal, you can notice here that if you go up to the 10 components in the kind of cyan here, then you see how far away you are from the actual cosmological signal. You really fit it out. So you've got a balancing act here to do, and this is not ideal. So this is something that we've only just published, and so it's not something we've solved yet. But hopefully, by introducing a scale dependence to that mixing matrix, we might get a better grasp on this. The other issue we've had is excess noise. So I said earlier that we kind of took it for granted that we'd be able to just figure out what this noise was and subtract it off. The problem has been is that our noise has been much larger than we thought it would be. So on the x-axis here, you've got frequency. On the y-axis, you've got a ratio. And that ratio is your noise value determined by one method, which is by looking at your, I'll go into it in a minute, but by looking at your intensity of your noise, you can look at the difference between two slices. And because the foregrounds are so smooth, it will be very similar between the slices. And so anything that's different, you take as a noise. And so you get one way of doing it that. And then you can also look in your Stokes speed channel, and that gives you another way of figuring out your noise. They should be the same. They're not. And so what we measured a lot of excess noise in our intensity data, which is the one we're playing with. And so you can see the ratio goes up to about 1.7. It varies by night, and we're not quite sure what's going on. And so this was figured out 5 years ago now, that we figured out this was happening. And it's taken 5 years to try and understand what it is, and we're still not there yet, but we've reduced it by I think a factor of 3 now. There's still some way to go, but we are getting there. So this has been a real challenge for the project. I don't think I've got time to go into edges, but since you've got Anastasia, I'm sure you know lots about it. But edges is great. It's given I'll just go very briefly through it. It's the other way of looking through this time is not by measuring how the ionization of the hydrogen imprints these bubbles. But if you go a bit earlier than that, what you can do is you can measure how that hydrogen warmed up, really. So when these first stars formed and they caused this hydrogen to change temperature in an appreciable way. So this is actually Anastasia's plot from one of her talks, which I've not managed to find in the paper, so I just had a screenshot of her talk. So sorry about that, but I have credited you. But it's just such a fantastic figure for showing that we had no idea what's going on, because the red is what Edges observed. Edges is a global experiment in the Murchison Australian desert, and grey are all the models that we knew about, and as you can see, none of them fit. Which is exciting. We don't know what it is. We can talk about what it is if you want. There's 3 different ways. I'm not going to go into the dark matter one. It could be the way they've modelled the foregrounds, because they modelled them with a polynomial, which, as we've discussed, has its issues. And it could also be an excess background, which I'm going to skip. You can ask me about it if you want. Yeah. So hopefully I've introduced you to one way of probing for these first stars, which is by looking at their footprints in the early universe in terms of the bubbles. We're not there yet. We are tantalizingly close. but as my PhD student reminded me just before this meeting, I promised him on his first day of his PhD that we'd have a detection. And it's getting a little bit close now, so I might be losing my bet, but hopefully it's not too far away. It's in in the next couple of years, maybe sooner. Shameless plug for the book. So yay, book. If you want to learn about first stars in a popular science format, then it's all in there, including the other ways we look at it, so stellar archaeology and everything like that. So thank you very much. Sorry for having to skip through a little bit at the end, but hopefully got most of it in.
Fantastic. Thanks, Emma. Yeah, right on time, basically. So that's good. That's great. So I will stop the recording at this stage, and we can move on to the question and answer session.